And we're just going to start with defining an inertial frame. So an inertial frame, this is a frame where Newton's laws apply. And usually we'll use the notation I. So usually we think of this as something that's like fixed in the lab or fixed on the ground for most intents and purposes, or I think Newton used the phrase fixed compared to the distant stars. Basically, you want it to be not moving, or for our purposes, and there'll be an origin, and then we've got some directions, and I'll usually use little n. These are giving unit directions that follow the right-hand rule. So n1 cross n2 equals n3. Maybe I'll just put that here. This makes this a right-handed coordinate system. And that's important for when we eventually, take cross products and things for mechanics purposes. So an inertial frame is technically an origin and then a triad of unit vectors, which define the three orthogonal or perpendicular directions. And with respect to this frame, you can look at the motion of particles. Okay, so we've got this is a particle. It's the path of a particle. Or if you want, it's a mass, m. And we'll use this notation for vectors. So this is r with an over arrow. So if this is a vector that changes with time. So let's say at this point, this is r. It gives the location at that time. And if we look at the instantaneous velocity of the particle, then we get another vector. So here's like the vector. This is the velocity of the particle. And the notation used by the book is to say it's the velocity with respect to the inertial frame. And so there's that little superscript at the beginning. And this is equal to the time derivative with respect to the inertial frame. So we get that superscript, time derivative of r. Right, and what's that? This is the usual derivative. So this is the limit as delta t goes to 0 of r at t plus delta t minus r at t divided by delta t. And at different points along the trajectory, the velocity will be going in different directions, but it's always going to be tangent to the path. Sometimes we'll use the notation of v without that superscript I, and we'll write this is equal to r over dot, where the over dot just means differentiation with respect to time. So that's shorthand. Shorthand for this derivative with respect to time and with respect to the inertial frame. You say, well, why do you keep emphasizing the inertial frame? You could take the derivative of something with respect to another frame, a moving frame, and that's what we'll get to later. That's why right now I'm emphasizing, no, this is all with respect to the inertial frame. So, okay, hopefully we've got this. You could talk about the path of a particle and then its velocity, which, because this is with respect to an inertial frame, we say it's the inertial velocity. And then what shows up in Newton's laws is acceleration. So we need to talk about the acceleration. Acceleration is just the inertial derivative of the inertial velocity. Maybe I'll just say inertial acceleration. All right, so this is time derivative with respect to the inertial frame of the time derivative with respect to the inertial frame of the location of the particle. Or we could say it's the time derivative with respect to the inertial frame of the inertial velocity. And what is this? This is the inertial acceleration. So as shorthand, we could say this is, just write the over dot. It's the first time derivative of the inertial velocity, or it's also the second time derivative of the particle location. Okay. Much of the time in setting up problems, especially for this first homework set, is just sort of writing the acceleration in terms of given variables, like the X, Y, and Z coordinates of the system, which, if you notice, I haven't even mentioned coordinates yet. This is kind of coordinate independent. All right, so now we're going to mention Newton's second law. It's really the main one. I don't even remember the first one or the third one. I do, I'm just kidding. All right, so Newton's second law, I'm gonna bring in a diagram from the book because it does it better than me. Whoa, what is that? It's a dizzying array of figures and things. Okay, there we go. Yay. Check it out. So it has this nice diagram in the book where it talks about, this is like the diagram of Newton's law. So we've got, this all starts with talking about the location of a particle. So this is a schematic of an inertial frame. So I'll put I there, and here's the origin. And here is the particle P. We'll say it's located at point P. So then here is like the path of the particle. But we want to first write where is the instantaneous location of the particle. So this is R P / O. That's the notation the book uses. So R P / O basically means the vector from O, so the origin, to P. And I'll tell you right now, the notation is cumbersome at the beginning, but it's very precise. So it helps when you're learning to be precise. Later, you could, drop things like, yeah, I know I'm always going to be referencing the origin, so skip it. But this is one thing I really like about the textbook I use is it's very careful about notation, especially at the beginning. Other textbooks, you're like, you get lost easily because they start dropping notation pretty quickly, and we don't want that. All right, so you've got that. You've got the inertial acceleration, inertial velocity of the particle, instantaneous velocity of that particle, which we could write as IV of P with respect to O. So this is the inertial velocity. And then we get the inertial acceleration, which, let me draw it in the diagram. It's not obvious what direction that's going to be heading. Let me just sort of draw an arrow to it. So that is the inertial acceleration of P with respect to O. I am running out of colors. All right. Now there's the idea of a force. Okay. So Newton's law basically says that the force is proportional to the acceleration, or if you want to vice versa, the acceleration is proportional to the force, and the proportionality constant is the mass. So the acceleration, that green vector, is always going to be in the same direction as the force, the total force on point P, particle P. So what is this? This is the sum of forces on particle P, or point P. So it's total force. And I mean, another way to write this is to introduce something that we call the linear momentum. So, whoa, that is not what I wanted. Linear momentum of particle P. And this is just the mass of particle P times the inertial velocity of particle P with respect to the origin. So there's these two equivalent ways to write Newton's law. I mean, I'm typically going to stick with the acceleration one. That makes the most sense to me. F equals ma, right? If you took dynamics, that's been drilled into you. F equals ma. So let's use that for good. All right, so this is this equation over here is the relationship, F P equals mp inertial acceleration of P. And what is there to be aware of here? Well, everything has to be done in an inertial frame. Like, what's another type of frame? Another type of frame would be a rotating frame, rapidly rotating frame. You couldn't just write Newton's laws and assume that they're going to hold in that frame, unless you're careful and you write all of the derivatives with respect to the rotating frame, but in an inertial frame. But we'll get to that. So this is sort of the main equation for what we'll do next. And this is a vector, this is a 3D, this is in 3D, right? This holds in 3D. We will start out just looking at it in 2D. Actually, we'll start out looking in 1D, just to get familiar with it. But this is, if you think of what is the acceleration, this is a second derivative of the position. So what we have is a Newton's second law is a second order ODE for the 3D position of the particle. And once you have literally turned it into some second order ODEs, so this is, so it's actually 3 second order ODEs. Think of R as being a vector in the inertial frame of X, Y, and Z. You'll get X double dot, Y double dot, Z double dot. 3 second order ODEs, they each equal something related to the force and the mass. And then you solve for it given initial conditions, the initial X position and the initial X velocity, and same for Y and Z. And once it's written in terms of second order ODEs, it can be solved, which is good. All right. So we're going to look at just doing Newton's law in 1D to get some practice. Unless I'll stop here and just ask, are there any questions No, okay. The Zoom format is kind of nice, right? Because then this is recorded. So if you want to, you could just step away and get coffee and then come back or watch it later. The problem for me is, when I mess up, now it's recorded and it's there forever. Yeah, sometimes I will actually change the notes before I post them if I notice some small problem, but I'm not going to change the recording. So if I get it wrong live, that's just how it is. Okay, so let's look at some 1D examples. What do I mean by that? I mean, we're just looking at motion in one direction. I'll use this phrase, 1 degree of freedom. And this is all from chapter 2 of the textbook, which I'll just call K and P right now. Okay, so we'll look at the simplest case, which is no force. So this is in the book as example 2.1. They've got these sort of quick things they call examples, and then kind of longer, more elaborate examples they call tutorials. And it's good to look at both of them because they'll really help with understanding the material and doing homeworks. So I'll just draw sort of the one dimension. We're looking at motion in this one dimension. We've defined an origin. And so here's our particle P. It's a mass. It's got a mass m, and we'll say the location is the distance is actually x. So our vector f equals ma just becomes a scalar, f equals ma, because we're in 1D. And we're actually looking at the case of f equals 0. So we're in free space. We're out there somewhere between the stars, and there's no force, just empty space. And how do we get A? Well, A is equal to the derivative of V. What's V in this case? Well, V is just x dot. So if V is x, the basically time derivative of x with respect to time, then this is d by dt of x dot, it's x double dot. So we could think of this in terms of A equals V dot or A equals to x double dot. Maybe we'll just think of it in terms of A equals V dot. So F equals MA becomes 0 equals M V dot. And that implies, here's this little arrow for implies, that V dot equals 0. So dV by dt equals 0. That means the velocity is not changing. So V, although it kind of should be changing with time, it is not. It is a constant. So that means it equals what it was at some initial time. All right. So that's something that we can deduce. If you're out in free space and you've got some velocity, I don't know, maybe you got it by some rocket thrust, you will just stay with that velocity forever. Your velocity won't change. The other way to look at this which isn't going to tell us really much new, but it'll kind of set the stage for other examples. Let's look at the x double dot. So this is x double dot equals 0. We could also write this as, so x double dot is d by dt of x dot equals 0. And what can we do with this? Well, we can turn this into, we'll do separation of variables and then integrate. So this looks like dx dot times 0 dt. Integrate both sides. Well, there's a big 0 in front, so who cares about this side? This is 0. You integrate this part, and you get x dot as a function of time plus some constant of integration equals 0. Okay, so we just did an integral. Now let's evaluate at the initial time. If we evaluate at the initial time, that gives us x dot at 0 plus c1 equals 0. That gives us that c1 equals negative of the initial x dot. Okay, so that means x dot t minus x dot at 0 equals 0, which is just another way of writing that the velocity at any time is what the velocity was initially. So in the absence of any forces, so for all time t, the velocity x dot is constant. The rate of change of x is constant. Okay, now that we have that, we could say, well, x dot at any time equals x dot equal, as it is initially. This is a constant. And remembering what x dot is, this is dx by dt. So again, we could write this as an integral. So write it in the differential form, dx, and then just multiply the other side by dt, x dot 0. That's a constant. It doesn't depend on time, times dt. Take the integral of both sides. And do the same thing where we'll evaluate for the constant of motion. And you'll get that xt equals x0 plus x dot 0 t. This is what we expect. This is our initial position in this one-dimensional world. This is our current position at a time t. And then x dot is just the constant velocity. If we were to plot, so along this along this horizontal axis, I'll put time. And along the vertical axis, I'll put our location, and along that one-dimensional, 1 degree of freedom. Then this is time equals 0 over here. At our time equals 0, we're at location x0. And we have a slope. The slope is x dot 0. So that's just graphing what this equation gives us, which is useful. It just tells us things are moving in space on a straight line with constant speed in the absence of any force. All right. So that's with no force. The next simplest case is to have a constant force. So let me just draw a line. Says, okay, we're kind of doing something new now. The next case is the constant force. We're still in a 1 degree of freedom world. So here's our origin. Here's the location of our particle P, which is, it's a mass, a point mass. It's kind of an idealized situation, a point mass M. And we've got a force. So let me kind of draw in a force. Actually, I think before I used orange. Let me see if I could use orange again. There we go, orange. So here's our force. And it is constant. So what might lead to a constant force? Gravity. So if the x direction here is, imagine it sort of pointed downward. So we've got a constant force going in a certain direction. There's certain stuff in electromagnetism that could give rise to a constant force. But think of those two, because we're thinking of action at a distance. Once you have things kind of pushing against it, you've got two masses interacting. We're thinking of forces acting at a distance. So gravity, electromagnetism, that's all good. All right, so the acceleration has to be in the same direction as the force, because we've got F equals ma, so we can just write that as A equals F over m. Okay, and then remembering, well, A is the it's the time derivative of the velocity, or if you want x double dot, then this equals F over m. Okay, let's use one of these forms and do an integral. Okay. Yeah, this one. So dx dt equals F over m. Put the dt over to the other side. F doesn't depend on time, so m also doesn't depend on time. So now when we write the integral, we can pull f and m out of the integral, and this is what we've got. So the next step would be just write what this is, fm, and then the integral of dt is t, and then we have a constant of integration. Let's evaluate that constant of integration. So we'll evaluate at the initial time. T equals 0. And what does that give us? X dot 0. We're just evaluating this equation, putting t equals 0. X, so the F over m times 0, and then we get C1. Okay. So C1 equals the initial velocity. All right. Then we'll just rewrite this. X dot t equals F over m t plus the initial velocity. And what is x dot? That's dx by dt. And now we repeat the process. Move dt over to the other side and integrate. So we rewrite this as an equation. Dx equals F over m t plus x dot naught. So the initial velocity, multiply that whole thing times dt. And now integrate. And what do we get? X t equals, now it's 1/2 f over m t squared plus x dot at time 0 t plus a constant of integration. We'll find out that constant of integration is the initial position. Okay, so now this is our formula. And just like above, we could plot just to kind of get an idea graphically how things are different in this case. Before, when f was 0, this term was gone, but now it's here. So now instead of having a curve with constant slope, the slope will change. So the curve, now we have a quadratic, something that's quadratic in time t. So if we had some initial position, our curve will do something quadratic. So x changes quadratically with time. Okay, 10, 20. Talking about forces. Okay, so we looked at the constant force. Now, kind of the next one would be a velocity dependent force. And the simplest type would be something that's linear in the velocity. So a velocity dependent force, I'll use this, F equals negative B x dot. And this is actually covered in tutorial 2.2 of the book. So what's an example of this kind of force? It's often an assumed force in different models because it is hard to measure friction. So we call this viscous friction or linear damping. And if you don't know if you have friction, this is a good guess to assume that you've got something it's a force that resists the velocity, right? Your velocity wants to go that way, and this is saying, no, I'm pulling you back. So B is some kind of constant parameter. What is also a viscous drag. This is also the form of the drag force when you've got a very, very small Reynolds number, so kind of microscopic things. I've done some work looking at pollen and fungal spores that are released from plants. So it's sort of like a biophysics thing. And there are actually plant diseases. So imagine like some infected wheat where things get forcefully expelled at very high velocity, like 30 meters per second. And we're talking about something very microscopic. So think of a fungal spore. So these things are on the order of fungal spore. This is on the order of like 10 microns. So they're really small. And as they move through the air, they experience a force that's like that. And they slow down like dramatically. So for all their effort of getting expelled at 30 meters per second, they go like a few millimeters from the surface of a plant. And then they hope that wind picks them up and spreads them to another plant. But it's always good to have these applications in mind. And anyway. Oh, and yeah, lots of people are studying this now with aerosols and spread of things through the air. Often this is the model that they're using for the very smallest particles. right? If you wear an N95 mask, that means 95% of things less than 2 microns, which means they're definitely in the regime where this force holds. Not the usual macroscopic F is proportional to the velocity squared. This is F linear in the velocity, so you get different kinds of dynamics. But it's also just something we commonly assume in engineering. So let me do the same kind of setup of a diagram. We've got our origin, got our particle P, which is a mass. And here's X. Suppose the X velocity, so X dot is going to the right, then this is going to resist. The force will resist because it's equal to negative B X dot with B positive. All right, so F equals MA becomes, and I usually like to write it as MA equals F because that's how we usually write differential equations. We have the thing that's differentiated on the left-hand side. So this becomes mx double dot equals negative b x dot. That's our ODE, okay? And we know x double dot is just the time derivative of x dot. So let's rewrite this, rewrite x double dot as d x dot dt. Let's move m over to the other side. And we can remind ourselves x dot is just the velocity. So maybe we'll just use notation of the velocity here, since we've got velocity on both sides. So we've got, let's go over here, dv dt equals negative b over mv. Let's do separation of variables. So on one side of the equation, that's where we want all the stuff that has v, and on the other side, all the stuff that has time. So we will rewrite this as dv divided by v equals negative b over m times dt. Okay, and then integrate both sides. B over m is a constant, so we can pull that out. You look up your handy dandy integrals of, what's the integral of 1 over something, and it's the natural log. So this is, and I'll do it all fancy, natural log VT plus a constant of integration equals negative B over MT. We want to get that constant of integration. So again, we evaluate at time t equals 0, the initial time. And so what do we get? We get ln v0 plus c1 equals 0. So this means c1 equals negative natural log of the initial velocity. Okay, so this becomes ln dt minus ln natural log the initial velocity equals negative b over mt. If you remember how to handle logs, if you have log of something minus log of something, you could just write that as the fraction log of this over log of this equals negative b over mt. Now take the exponential of both sides. And what do we get? We get, if you take the exponential of the natural log, then you just sort of get the argument itself. V over V0 equals exponential negative B over MT. Or let's write this as VT equals the initial velocity, e to the negative B over MT. So the velocity decreases exponentially. Yeah, if we were to plot this with time. Here's our initial velocity, and we get decreasing exponentially. Exponential decrease of velocity. And that rate of decrease is related to negative b over m. Okay. Now, if we want to find out what the position is, now we have to integrate again. So remember, what was v? V is x dot. And here x dot is changing with time. And let's just remind ourselves this is dx dt. Okay, so we've got dx dt equals the initial velocity, which is just a constant, times e to the negative b over mt. Separate variables. What are the two variables here? X and t. So that means everything that depends on x, and it's just dx, it's over there. And then everything that depends on time, it's over here. V0 is a constant. The initial velocity is a constant, so we can pull it out of the integral. Now we're going to integrate both sides. Xt equals, you could look that up, or hopefully you just sort of know it. I don't know. This is going to be that. Write it the same way, at least, negative b over mt. And we pick up, since we already had a first constant of integration, I'll call this C2, the second constant of integration. We find C2 by evaluating this equation at t equals 0. And what do we find? This will give us C2 equals the initial position plus m over b v0. Now we put all this together to get our basically our solution for x is a function of time. X is a function of time equals x0, the initial x plus m over b v0, 1 minus e to the negative b over mt. Now, what do we expect? We expect if something, let's say something gets shot out with some initial velocity, and that initial velocity is, the velocity is decaying exponentially with time. As the velocity is decaying exponentially with time, the particle is going less and less far with time. So it'll probably asymptote to some final distance that it'll take forever to get to. And yeah, that's what happens. So we have, let's just plot, just like we've done before, the position x as a function of time. Here's our initial position. And this thing is shot out in a positive x direction. And it just sort of asymptotes. Okay. It asymptotes to this thing, we'll call it xf. And what is it? It's x0 plus m over b v0. What do you know? It's that second constant of integration over here. That's not a negative in front. That is just a mark. So that means it traveled a distance m over b v0 in the long time limit. If you want to imagine what it would look like in terms of, here's x, if something got shot out at this location x0, and then let's just put equal tick marks. So every second we put where the location is. Okay, here it is after the first second, then after the second, third, fourth, fifth. It's kind of asymptoting to something, and that's this XF location. So what we literally see, if this has been done in experiments where you can kind of shoot out little aerosols or fungal spores or something, and so they will like quickly go somewhere and then they just fall straight down and then land on the floor. This is in still air, right? In still air. If there's something else going on in the air, then this will, you know, quickly get to here and then maybe do something weird, Brownian motion due to turbulence. But in still air, it'll just sort of get deposited at some known location, which is B over M, the initial velocity. All right. Where are we in time? Oh yeah, we can do this. Okay. We're gonna do one last example. So what do? Zero force, constant force, velocity dependent force, and now position dependent force. And this is what we will end with. And then next time, I think we'll look at things in 2D, so planar motion. So there's motion in X and Y, not just X. All right. Position dependent force. What's an example of a position dependent force? Well, like gravity in orbit around the Earth. We don't have to be as exotic. We see this all the time. This is like vibrational motion, the motion of a spring. So a spring. So the simplest thing, just like before, we looked at something that was linear in the velocity. Now we'll look at something that is linear in the position. And later we could look at more exotic things. But so F equals negative kx. So this is x is measured with respect to an equilibrium. Something of this form, where k is a positive constant, we would call this a linear restoring force, or just restoring force. So for example, the linear restoring force of a spring, or some element that acts like a spring. And underneath it all, mechanically, we'd say this is due to elasticity. So if I have here's a wall, and then I'll use this accordion-looking thing to describe the spring. Here's my equilibrium location. So if I started there, the spring wouldn't move. Let me put a little mass. There's our mass, or particle, P, and we're using X to describe the location of our the displacement of the mass from equilibrium. Okay, so as a linear restoring force, it's pointing in the opposite direction of X. So if X is pointing to the right, F is pointing to the left to restore equilibrium. All right, so M A equals F. In this case, we have M X double dot equals negative KX. And this has gone over in the book. It's tutorial 2.3. So we should have an idea of what would happen. This would be called a sanity check. Like, what does your intuition tell you? You pull on the spring, and then you release. I guess you're pulling on the mass, and then you release it, and then you expect it'll oscillate back and forth, right? So we'll get oscillatory motion. Oscillatory. or we also call it simple harmonic motion. And I mean, I'll just sketch what we expect. Like if you started with some initial position, you expect this to be sinusoidal. So this is in the absence of damping, you expect this to be sinusoidal. And from here to here, it'll be some period t, and there'll be periodic motion. And this is in the idealized case of no damping. Of course, if you add damping, so mx double dot equals negative kx minus, let's put it in red, minus bx dot. Well, what do we expect? We expect that this damping will lead to the oscillations getting kind of damped out, right, with time. There's going to be some kind of envelope of the amplitude that gets decreased. So red is with damping over here. How do we analytically solve this? We need to use some vector notation. So and this is where I'll end, we're going to define a vector. I'll call it y. And it's x and x dot. Okay. And what is y dot? Y dot equals x dot x double dot. What's our ODE? Our ODE, so just first without damping, this is x double dot equals negative k over m x dot. So we want to write this in this vector notation. Y dot equals, it actually equals a 2x2 matrix A times y. And this 2x2 matrix looks like 0, 1, negative k over m, 0, x dot. So this is A. And this can be solved. The solution for a linear ODE with constant coefficients is y as a function of time equals e to the at y 0. So this is the exponential of a matrix. If you haven't seen the exponential of a matrix, it's looks like this. So this would be the 2x2 identity matrix. And then a times t plus 1 over 2 factorial, a squared, t squared, plus, and then the rest of this Taylor series expansion looks just like you would for any normal exponential. So that's the solution. And this ends up giving you, we don't have time to look at the rest of it now, but it gives sinusoidal motion with time. All right, so that is it for today.